First up is Irene Moskowitz, and so I will pull up her talk now. And if you want to come on up. And, oh no. There you go. Center view. There you go. And that is a laser pointer if you want it. Otherwise, the floor is yours.
Thanks. So hi everyone. I'm gonna change gears a little bit from I think some of the stuff we've talked about this morning and talk about how I'm using machine learning techniques to do astronomy. I'm a grad student at Rutgers in my final year, working with Erica Weiser. And the problem that we're mostly focused on is how to get photometric redshift estimates so we can do cosmology with large imaging surveys. Oh, it says the screen is not shared.
Indeed. There is. Now I'm being silly. I should be host. Okay, good. Camera doesn't want video anymore. Okay, that is definitely correct. Okay, let's click out of this for a sec. Okay. Recording. Goodness, what am I doing? Oh my gosh. It was completely highlighted and I just completely did not see it. Okay. Thanks for pointing that out, Andrea, online. All right, good to go. Put you back in presenter. All right, take it away, and apologies.
All right, so if the title was a little jargony, we'll get there. But to start with a quick outline, I'll give a brief introduction to the Rubin Observatory, and then I will talk about my science goal, which is measuring cosmology with galaxy clustering weak lensing. The problem that, well, there are many difficulties, but the one that I will focus on is measuring photometric redshifts and talk about a few ways that I have been investigating uses of machine learning to try and address the difficulties that we're having, and then I'll end with some initial science results. Okay. Okay, so the Virasi Rubin Observatory will operate the legacy survey of space and time. So Rubin and LSST, I will say both of those during this talk, they are, for all intents and purposes, the same thing. The observatory saw first light last spring in June and began official operations in the fall. And it will take observations with the 8.4 meter Simoniu Survey Telescope, which is equipped with the LSST camera, which is in the Guinness Book of World Records as the largest digital camera ever built. And over the course of the 10-year survey, it will observe the entirety of the southern hemisphere sky and will get a new total picture of the sky every few nights. It's expected over this 10-year survey to observe tens of billions of galaxies, hundreds of thousands of supernovae, stars, asteroids, comets, more astronomical data than any other survey has generated, or any other telescope has ever generated in the history of astronomy. This will be terabytes of data every single night. So this obviously provides lots of challenges for people who want to analyze this data, just trying to even use it all. But my specific science goal is to use these tens of billions of galaxies that we will observe to learn about cosmology, especially the dark energy equation of state. And we do this, or I do this, using two specific probes. The first one is the large scale structure. So this map over here, this is from the 2DF survey, and it is showing each of these blue points is a location of a galaxy in this map. And you can see that it's not random. There's structure here. There's filaments, there's clumps, there's stuff going on. And this structure comes from cosmology. So what we want to probe is the matter power spectrum, which basically tells you how matter is distributed on different size scales. but all we can see are the galaxies. So of course there's dark matter in the universe as well, and we can't see that. But we want to know how all of this matter is distributed. Luckily for us, galaxies form in dark matter halos. So if we look at the galaxies, that is what we call a biased tracer of the total matter density field. So the galaxy density field is related to the total density field through some bias parameter. And what we actually measure is called the galaxy clustering 2-point correlation function. And so that is essentially, the 2-point correlation is the statistic that is telling you the excess probability over a random distribution that you will find two galaxies separated by some distance x. So if you had a random distribution, your 2-point correlation would be flat. And any difference that you have from flat is coming from cosmology. It's how our universe has evolved over time, is that's giving at the 2-point correlation some shape that is not flat. The second probe is weak lensing. So if you are looking at these galaxies that are far away, the photons from those galaxies are traveling through space, and they are being deflected by this large-scale structure as those photons travel to you. And so weak lensing is basically describing the slight distortion in the shapes of the galaxies that you observe versus their intrinsic property. And so this is an extremely exaggerated illustration of what's happening. So if all of the background galaxies were these nice circle spirals just intrinsically, the weak lensing is giving them these elliptical shapes. And unlike galaxy clustering, weak lensing is sensitive to both dark matter and galaxies along the line of sight, so we don't have to worry about galaxy bias like we do with galaxy clustering. But there are other sources of systematic uncertainties, such as intrinsic alignments. So that's where galaxies that are forming in the same environment will have intrinsically similar shapes to each other. And that is not from weak lensing. That's just because they actually do look alike. But cosmic shear is now the 2-point correlation function that tells you how correlated galaxy shapes are when they are separated by a distance x. So if you have two galaxy pairs, you have galaxy pairs, and you're correlating the shapes now. And again, you're comparing this to random. So any difference from random is, again, because of your cosmology. So weak lensing and large-scale structure are complementary probes of cosmology. They have different systematics, so we like to do them at the same time. But in order to do either any of this, we need to know where galaxies are. So it's really easy to look at the sky and you say, well, there's one over there, there's one over there. So that's two of your dimensions, but we also care about how far away they are. And that is the redshift. So this is the particular difficulty that I work on in relation to cosmology with LSST. And so if you wanted to get a really nice, accurate redshift, you would take a spectra. You would look at your spectra and you'd say, well, here's the Balmer break, here are some oxygen lines, here are some hydrogen lines. You know what wavelength those would be at if they were right next to us. And so that difference between the wavelength that you measure those features at and what you know they are intrinsically at tells you the redshift. LSST is an imaging survey. And like I said, it is the largest imaging survey we have ever had. So spectroscopic follow-up of these tens of billions of galaxies will be extremely limited. So we cannot use spectra. We have to rely on photometry for most of the redshifts for these galaxies. And this little movie is showing basically why this works. So the black line is an example galaxy spectrum, and these are the different filters that LSST has. And you can see that as the spectrum gets redshifted, the amount of flux through each of your filters is changing in a physically motivated, predictable way. It's very complex, but it is predictable. And so because it's predictable, we can use the photometry, the flux through each of these bands, to estimate what the redshift of a galaxy is. And there are two main ways that we can do this, two broad categories. The first is template fitting, where you have a library of example spectra that you basically redshift. You know what the filter transmission curves of your telescope are, so you can generate what the photometry would be for each of the spectra in your library at a given redshift, and you find the best fitting match. This is nicely physically motivated, but it's limited by the fact by template mismatch. If you don't have the right templates in your library, you won't get accurate redshifts out. And we know we don't have accurate templates in our library because we don't really know how galaxy formation works at high redshifts. And we know it's different from low redshift. All of our templates are from low redshift. So there is going to be this mismatch. The other category is we can use machine learning. So if you have some training sample of galaxies with highly accurate spectroscopic redshifts, You can use that to learn a relationship between the redshift and the photometry, which you then apply to your data that only has photometry. I think probably most people in this room know that if you want to do machine learning, you need a representative training sample, because if you don't have, if your model hasn't seen something before, it doesn't usually know what to do with it, and so you'll get kind of nonsense out. And that is the issue that we will have with LSST. LSST is the biggest, deepest imaging survey we have ever had, so we do not have representative spectroscopic training samples. And if we want to see sort of an illustration of how bad this problem will be, I've used a simulated DC2 catalog. So the DC2 catalog was made to look like our expected LSST data, which we don't actually have yet. And I've done some forecasting for photometric redshifts using this. So the first state is our ideal case where we have a fully representative training sample. So I just randomly split this into training and data, and I trained my model, and I got some photometric redshifts on the top here. So we have the photo Z estimate on the y-axis, the true redshift on the x-axis, and you can see that most of these galaxies are falling on this one-to-one line. So the photo Z is basically the same within our uncertainty tolerances. That's these solid black lines of the true redshift. So that's good, that works well. This is unrealistic. So in reality, spectroscopic training data will be biased towards brighter, redder, lower redshift galaxies than LSST will observe. And so if I make a training sample that now looks like spectroscopic data compared to, this is our data set, LSST-like data, and this training sample covers like here-ish. So there's this whole big high density region that really doesn't have any coverage in the training sample at all. And so if I redo this whole exercise and get new photo Zs, now on the bottom, this is what I'm getting. So overall, we have an outlier fraction of about 50%, and kind of anything above a redshift of 1 is basically a catastrophic outlier. So this is not really good for doing precision cosmology with LSST. And this is the problem that I have been working in my PhD thesis to try and solve. So we need to find a way, we need better photo Zs if we want LSST to be a success for cosmology. And we need to do it without getting a bunch of really deep spectra. LSST has started operations, so it is too late to sort of, to do that. So we need a way to do this that doesn't involve getting more spectra to make our training sample actually representative. And so I've been working on augmentations. What if we just put simulated galaxies into our training sample to cover this region that we don't have data for? And so in order to test this, I have a second simulation, Buzzard, that I've been using for augmentation. And I have a few pretty simple selection criteria that we've been testing. So the first one is, let's just pick out of our augmentation set, let's pick faint galaxies. There are a lot of them, will be a lot of them in LSST. There are not a lot in our spectroscopic training sample. We can pick blue galaxies. We can do a combination of faint and blue galaxies where we fit sort of the shape of this color magnitude diagram for the training sample, and then we pick augmentation galaxies from this region. Or we can do high redshift. So the reason everything above a redshift of about 1 was a catastrophic outlier is because the training sample only really goes out to about a redshift of 1. So let's just pick galaxies that are at higher redshifts than that. And then we can do a combination. So high redshift with faint, with blue, with the, any of the other photometric criteria. We also have the problem that simulations do not represent the true color redshift relationship of the universe. Simulations aren't real. I'd be out of a job if we were new enough to make them really true to life. So is there some kind of post-processing that we can do to these simulated catalogs to sort of bridge this difference in domain between the simulations and real life? Complicated by the fact that we don't actually know what the true color redshift relationship is at high redshift. So we want to make our simulations more like real life, but we don't actually know what real life is. And there were a couple of different ways that we tried to do this. The simple way, where we just shifted all of our photometry by a single value so that the median magnitudes or colors of our simulated distribution overlapped with our data. So we're basically trying to make the distributions of the photometry look the same. And in this case, our simulated galaxies for augmentation, they keep the same redshift that they got out of the simulation, but they get new photometry. Or we tried a more complex way using a two-step series of normalizing flows. So the first one, we trained a conditional normalizing flow based on our simulated data, because this is where we know the redshifts. So this is based on the photon. What is the probability of getting a redshift given a set of photometry, which we need simulations for? So we train that. And then the second normalizing flow generates photometry that looks like our data. So now instead of just simply using this second buzzard simulation for augmenting, we've generated new photometry based on the second normalizing flow that looks like our data. And then we use the conditional normalizing flow to generate a redshift for that photometry to look more like the buzzard redshifts. Turns out the simple way was actually the better way, at least in this case. So the results that I'm going to show are using this. So the real question is, does this actually work? And it was a pretty resounding success. So these two are the same plots that you've seen before, just now side by side instead of on top of each other. And then the augmented training, we've used a combination of the redshift, color, and magnitude, so all three selection criteria. And then that shifting, we shifted all of the augmented magnitudes, like on the last slide. And we have a 50% reduction in the outlier fraction just right away. And if you consider the fact that we don't actually start with 0% outliers when we have the representative case, we're actually 70% of the way back to this ideal case. So this is pretty exciting. This works really well. But we can also think about the fact that 25% outliers, which is what we've got so far, still isn't really good enough for precision cosmology. So we'd like a way to try and figure out which of these galaxies are going to have bad photoses. So LSST, with tens of billions of galaxies, we do not have to worry about Poisson noise. We have really large number statistics. So if we can find those galaxies with bad photoses and toss them out of our cosmology sample, we can have a purer sample that will hopefully get us better cosmology. And so we've been using neural network classifiers to do this, to estimate a confidence. If you give it a galaxy with a photo-z estimate and some photometry, it gives you a confidence back that it has a good photo-z versus a bad photo-z. And this plot is showing the discard rate. So we throw out galaxies with low confidence as a function of these same redshift plots. So the dark colors are low discard rates, and the bright colors are high discard rates. So it's doing a pretty good job, especially at the lower redshifts where we still have representative training of saying these ones on the diagonal actually are good photo-z's, and these ones on the off diagonal are bad photo-z's. It does a little bit worse at higher redshift because we still have non-representative training samples. So this is all using that. Still has the same issue. But it does a really good job of actually identifying which galaxies are probably don't have good redshifts. And so we won't have this information when we have actual LSST data. So we want to make sure that this actually works well while we can. So let's look at a couple of initial actual cosmology results, because that's what I ultimately care about. And so this here is showing the galaxy clustering 2-point correlation functions using each of these three training samples, so the representative, the unaugmented, and the augmented. And especially if you look in these intermediate redshift ranges, you can see that the representative case in the yellow and the unaugmented case in the purple have pretty different, you get pretty different measurements of this correlation function. And the augmented one is much closer to this, what we would ideally like to have, than the unaugmented is. So we are seeing already that this is hopefully actually giving us better cosmology in addition to just better photoses, which is what we really care about. And so then if we turn these correlation functions to try and actually get some cosmological results out of them, these are very preliminary results. So I'm looking at W, which is the dark energy equation of state parameter, and the dark matter energy density. And so the same color scheme as the last slide. Yellow is our representative case, purple is our unaugmented case. And you can see that we're actually doing a really good job of reducing bias, particularly in the dark matter energy density. Not so much in the equation of state of dark energy yet, so still working on ways to see if we can maybe improve this to actually get all of the parameters to do better. But there are some nice hints that this is actually working pretty well. So I will just leave up a summary slide. The success of LSST cosmology critically depends on having accurate photoses. And training sample augmentation and this neural network sample selection process are showing that they have the potential to reduce bias in our cosmology. Of course, everything I've shown today has been with simulated data because we don't have real LSST data yet, and real data is messier. But the Rubin data previews, so the first data preview came out last spring. The second data preview is forecast for this year. Give us a chance to start piloting these techniques with real Rubin data. And so I've started working on this training sample augmentation a little bit with data preview 1. And I actually have some initial results in a session on Thursday, if anybody is interested in that. But thank you. I'll take any questions.
Okay.
On the plot where you had like the reduction, it was in like yellow and purple, back one more, or maybe one more. Yeah, this is, yeah, I don't remember, this part right. Do you know why that there's like a horizontal bar that's kind of going along, near like photos 1.5?
Yes, well, we're pretty sure we know what's happening. So the Photo Z code that I have used to estimate the redshift, it's called FlexiBoost. And that is a conditional density estimator. So it looks for, in your training sample, it looks for sort of high density regions, even if they're not high numbers of galaxies there. It looks for high density regions, and it will sort of preferentially assign Photo Zs to those high density regions. And so with the augmentation selection criteria of being at high redshift, we have a high-ish density of objects at a redshift of 1.5 now in our training sample. And so we're getting a lot of estimates in now at that redshift. So we're trying to figure out a way to impose another criteria that sort of smoothly selects galaxies at high redshift so that we don't have this artificial overdensity here. So that's what we think is happening.
I think that was really interesting, Irene from the University of Kansas. So you said the complex method you tried using didn't work as well, and I'm curious if you can speak about how much worse it performed, and also my secondary question then would be that your complex method, using normalized flows, you should get some sense of like a redshift posterior, I would imagine. So, was it that the posteriors were more broad, indicating that you just can't really constrain redshift, or they just roasted kind of?
Yeah, so it wasn't like really bad. It just didn't really help very much over not using it at all. But the reason we think it didn't work so well is because we're basically trying, essentially what we're doing is kind of reproducing the color redshift relationship of the simulation, just at a different photometry range than the simulation originally has. And so because we want the real color redshift relationship, not the simulated color redshift relationship, it's turned out that wasn't helping very well. So we're trying to think of ways that we can maybe use the information that we actually that we have to try and do this more logically to try and actually get better results. But the two-step process that we have right now is essentially just saying, well, we're moving the photos, the photometry distributions, but we still have the same color redshift relationship because the redshifts that we're estimating are coming from the simulation.
Thank you very much.
Free question? I've got one quick one on the cosmological parameter slide, the Marty slide for you. Yeah, that one. I would imagine that the purple, the unaugmented, has bigger blobs there because it's got a bunch of catastrophic outliers that you can do all kinds of wacky numbers. But do you have a sense of why the augmented is significantly narrower or smaller in extent than the representative sample?
So part of it is just because this is using a very small subset of the simulated data that we have, because this sort of MCMC sampling takes a very long time. So before I apply it to the entire simulation, I've just been testing things to make sure everything runs and is working the way that we expect it to. So part of this is just because you can't really do good cosmology with 1 square degree worth of simulated data. So the we think for this slide, we think the location of the parameters, like where they're centered on, is about accurate, but the actual shape and size of the contours is not.
Makes perfect sense. Smarter to test everything on good lesson there. All right, let's keep rolling.
Okie dokie. Next up, get out of here. Oh, there we go. All right, here we go. Next up is, I believe, a first-time speaker at ATDS, Andrea Urban. I've been trying to get her to speak for a while, and she finally agreed. So I'm very excited to hear from her. Also, the topic she's speaking on is something that I personally now do work in, so I'm super stoked for this talk. I'm stoked for all the talks, let's be honest. But okay, so I will stop sharing, Andrea, and you can take it away. Oh. Let me pull this up onto our screen.
Can you see the screen?
Yes, we can see your talk.
Okay.
All right, take it away.
Okay, it's loading. Okay. Hi, I can't see anyone. Let me see if I can move the thing over. It helps to see people. Okay. Hi, it's so great to be here. The talks have been really awesome, and thanks to the organizers for organizing this and having me speak here. It's been really great to hear all the talks, and just want to say astronomers are pretty cool and still true. So I'm going to talk about the work I do at a utility company looking for electric vehicles. So a little bit about myself. So in academia, I got my PhD in astronomy from UT Austin. Studying star formation, I ran simulations in Fortran to study how stars form. And then after that, I went to do a NASA postdoc at JPL. During that time, I started doing adjunct teaching on the side, and I transitioned into teaching and education. And I worked at an educational technology company building their astronomy curriculum. And then during that time, I had started hearing about data science, and some of my fellows in grad school had transitioned into data science, and it was interesting to me. So I did some research into it, and I spent about a year learning Python from, moving from Fortran to Python and SQL. I learned all about the machine learning vocabulary. Got some engineering skills, learned a little bit of Git. And then I was accepted into the Insight Data Science Fellowship, and that was a great experience. I did not get a job from the fellowship, but I did meet a lot of really great people. And one of those people had a job, was able to find their own job in data science, and their company was hiring. And so they brought me on board. And so that's how I got my first job in data science. I worked initially at a small consulting company, less than 10 people. We worked with telecommunications company, a coffee company, in marketing. I mainly worked in Python and SQL there. I was there for about a year, and then I transitioned to a cybersecurity company where I look for cyber threats and DNS protocol. I mainly worked in AWS and PySpark, and I was basically learning PySpark on the job and AWS. So that was a fun experience, and I learned a lot. But now I work at PSC, and I've been there for about 4 years now. So what is PSC? So Puget Sound Energy is Washington State's oldest local energy utility. So in the map of the US, there's Washington State in the corner, and in the northwest corner of that, there's Puget Sound, where there's all this water everywhere. And that's our service area highlighted in red, yellow, green, and orange. Um, and so Seattle is the biggest city in the area. I live in Tacoma. PSC provides natural gas and electricity to these regions, just depending on where you live. In Tacoma, I only get natural gas from PSC. My electricity comes from my Tacoma Public Utilities. PSC is interesting in that it's a company, it's an investor-owned utility, meaning we make profit. However, our rates are set by regulatory agency, so we're only allowed to make so much profit. So every year we have to make a case for why we should raise the rates in order to provide our customers with more energy efficient rebates, or we need to build a new solar plant. So it's an interesting trend, it's not really, it's a company, but it's also a utility, a public utility. So it's an interesting place to live because there's no competition, right? There's only one electric company you can use, so customers have to use us. So it's this interesting place to live in terms of working at a company. So who is our customer? So of the 8 million residents in Washington State, about 1 million of them are electric customers with PSC, and about 800,000 are natural gas customers. So that's the PSC customer base. Next, I'll talk about the motivation for the work I do there. So electric vehicle charging is expected to continue to grow, and the demand on our electric infrastructure will also increase because of that. On the left, there's a plot of or a map of the US from the Department of Energy showing where PEV or plug-in electric vehicle adoption will be happening in the future. There's a lot of it in California and a lot in Washington State where PSC is located. On the right, there's bar charts showing the growth of electric vehicle percentage from the Department of Licensing, or the DMV in Washington State. On the top, there's the 10 counties in PSC service territory. So we're up to about 4.5% EVs in our service territory. But of the top two most populous counties, it's about 6%. And it's expected to continue to grow. So it's growing, but if you notice, it is a small number. It's less than 10%. So, why are we worried about, less than 10% of our customers are, charging their EVs? So I'm going to show a little bit more about that in the next few slides, but basically electric vehicle charging puts stress on the electric grid, particularly our distribution transformers. So just a little background about electricity. So on the left is your red generating station. So these are your power stations, your power plants, your nuclear, solar, wind farms. They create the energy, which is then transmitted across the transmission lines in the blue, and then eventually it goes to the neighborhoods. And so you'll see in the green, you'll see these and the distribution transformers, which is what I'm talking about. Those are those cylinders that you see on electric poles. They usually serve about 10 customers are hooked up to each one of those 10 meters. And so what we're interested in understanding is how many electric vehicles are being charged on a transformer, because that can really stress and overload the transformer if that happens for a long time. So for example, if we have just one EV on a distribution transformer, we put them up there so that they can handle some stress and overloading. But if you have an EV, your neighbor's going to want to get an EV, and maybe your other neighbor's going to want to get an EV. So you're more likely to get more EVs on the transformer that's already overloaded if you've already got the one. So this is why we're interested in understanding where the EVs are in our service territory, because of their effect on the distribution transformers and the possibility of failure and needing to replace them earlier than we expected. So like I mentioned before, we're trying to detect EVs, and this is a highly imbalanced problem. So there's not a lot of EVs, but we really want to find them. We want to know where they are. And because it's an imbalanced problem, I'm just going to throw some data science and machine learning vocabulary in there, but like accuracy is not really a true measure of your model performance. So over here, I don't know if you can see my arrow, but I can basically, so this is a confusion matrix. And if I build a model and predict that all of my customers do not have an EV, and there's actually just 5% of them do in the true reality. But if I just predict that no one owns an EV, then I can get a 95% accuracy. And that sounds great, but if you calculate other metrics like precision and recall, it's actually pretty bad. So accuracy is not what we're looking to optimize when we build our model. So a little bit about how I went off to build a model for detecting electric vehicles. So So for every meter on the side of a house, it sends back the amount of energy used for every 15-minute intervals. So it's time series data we have, and you can see an example of that on the bottom here. And so for a given day, the total usage is shown here in green, bluish green for a customer, and then the EV charging is shown here in orange. And so we have this EV charging usage data because a few of our customers, less than 1,000, enrolled in a pilot program where we were able to collect specifically just their EV charging usage data. And so we're able to disaggregate that from the total usage. And so this is the source of our true positives when we build our model. My team also regularly surveys customers, so we have some idea of who does not own an EV. So we also have some true negatives as well from just survey data. So looking at the data, you might think it's a time series problem, but we're really not trying to predict like when is a customer charging or what's going to happen in the next time period. It's actually a classification problem that uses time series data. So I have to use this time series data and do some feature engineering in order to create the features I want for my classification problem. So some of the features I found by doing exploratory data analysis is that most of the charging has this shape of this square shape, where it's this big ramp up, sustained usage over a long period of a couple of hours, and then a drop back. And this jump and this high sustained usage is actually what is likely to be causing transformers to fail, because it's such an unusual behavior, and it's a lot of usage for a long period of time. So this is one of the features I built into the model. I also didn't want my features to be dependent on time of day because customers should be able to charge anytime. We do find from the data that most charging lasts about 2 to 6 hours. So that was just another feature in the data. And so once I was able to build the features for my model, I basically just I just tried a random forest model as my first one, and it gave me good enough performance that I was happy, and I just kind of stuck with it. I haven't even tried any other models because it's good enough for what we need here. So here's my confusion matrix for the model. And so the accuracy is great, which is, good to have, but, not what we want to look for. Really focusing on making sure our precision and our recall are high. So precision basically tells you of the things predicted to be true, how many did you get right? So, of these things predicted to be true, these 416 plus 60, 416 are right. So we got 87% precision, and recall is 76%, which basically says of all the things that are actually true, how many did you find? So we found 416 out of this total here. So, we were pretty happy with this for first pass. And so I took the model, I applied it to all my customers using all the data over all time back to 2021 to show, what is our penetration of EV charging among our customers. And we found it to be about 75.5% for level 2 charging among PSC electric meters. So, that was a really great result, but you're only looking, this is the amount of data going into the training set and the test set is really small compared to the million customers we're looking at. So, and those customers who signed up to be part of our training data set were unique, they might be unique customers who are, different from your typical PSC customer. So what we did is we ran a validation survey where we took 10,000 customers predicted to own EV and 10,000 predicted to not own an EV based off of the model. And we sent them a survey to see, like, do you own an EV? Just to see some sort of validation of our training or of our model. And so this is the confusion matrix of that. And here are the performance metrics. And so you can see that, the survey is not that far off. It's still got high precision and recall, which is what we want. So we felt like we did a pretty good job here. And so that's it for my talk. So I just wanted to summarize a little bit. So I built an EV charging model to find EVs among our customers. The model has high performance metrics. Even though I was working with imbalanced data, I was able to perform validation on the model with survey results and showed that the model was robust. For next steps, we're of course building a dashboard to show our model output to our stakeholders, and this will help them in their decision-making process when they're upgrading their transformers. Additionally, the load forecasting team, so the folks who try to predict how much load or usage we'll need in the future, they're also interested in this model and next steps for the model of disaggregating the usage of EV charging. So when does a customer charge and how much are they charging their EV? How much energy goes into charging their EV? So thanks. It's been great to be here. And the talks have been amazing, and thanks for having me. Open to questions if there's any questions.
Hi, this is Tony calling from Carnegie Observatories.
I can't hear you at all.
I kind of would naively assume that the important thing here is just the load on the grid in any geographic location at a given time. So I'm curious, like, why specifically taking out EVs rather than just kind of building a general model agnostic to what is being charged or what's using the grid at any given time? Like, yeah, I'm just curious if you could speak a little bit more about why a specific EV ownership type model might be more beneficial than just like a general load model.
So yeah, I understand. So your question is about why is EV charging detection versus just a general load model more beneficial? I wouldn't say it is. So we do have a whole team in our company that does the modeling for the load prediction, load forecasting for the whole grid. And so they're the team that decide, as EV usage grows, how many more power plants do we need to put in our system? How much more power do we need? So it's important for that. So that team works on that. The project I was interested in is for particularly like how does EV charging affect those distribution transformers? Because they're going to overload EV charging will overload the distribution transformers and cause them to fail sooner than we expect, because it's an increased load that is not expected in a very specific and targeted location. Does that help answer your question?
Yeah, absolutely. Thanks a lot.
Other questions? Well, right here. Hi, thanks for a great talk. Kurt Hamlet from the University of Kansas. I'm curious if you thought of approaching this from a anomaly perspective, where you have so much data of normal power grid usage. I was looking to add if you were to project that usage into some representative space that perhaps the EV usage might sort of lie its own little part that's base.
I'm sorry, I couldn't really understand the question.
So I'm just curious if you've thought of or tried tackling this problem also from a anomaly detection view, where you have so much data clearly of normal non-EV power usage. If you were to try to tackle from some novel point of view, that perhaps these would lie in their own region of some parameters to base.
So I think I'm understanding, like, if I try to do something like detections of other things besides EVs and more generally detecting unusual things, is that right?
Yeah, so just like anomaly detection in general.
Anomaly detection.
Yeah.
Yeah. So I haven't done it with anomaly detection, but that's a good idea. And I think, well, let me think. So we do have anomaly detection algorithms that we run every day that basically detect if for things like fraud, like customers stealing power, you know, like this meter is broken, but it shouldn't be broken. So we do have separate algorithms that detect like anomalies in terms of that kind of thing. But nothing like, you know, this customer has been using way too much energy than they're expected to use. We haven't done anything like that that I'm aware of, unless it's related to like detecting fraud or, you know, issues with billing. Um, but that we have done other types of detections of like heating and cooling systems, trying to find out which customers have a gas heater, which ones have an electric heater, because there's this whole idea of electrification. We want to move away from natural gas. And so we want to find the customers who use natural gas heating and maybe give them incentives to convert to electric heating. So we do have other kinds of models that do other kinds of detections.
Thank you very much.
Yeah, I have a question. Did you get a chance to inspect the errors of your model and try to tell a story to yourself about what was going on? Like, did you find new populations of people who like running, I don't know, training machine learning models like Christopher or you know, or you know, I don't know, crypto bros? Like, did you see anything interesting in the errors?
Yeah, so I initially in the model, when I trained the model, I was looking at like, well, where are the, you know, the false negatives? What, you know, what am I missing? And as you would expect, most EVs, at least in the Seattle area, are Teslas. And Teslas have the charging pattern that I showed in the image before. But the ones that I was missing, the cars that I was missing, they were actually more likely to be a Nissan Leaf, which have a different charging pattern. They have more of an exponential ramp up rather than like a straight sharp ramp up. So that's why my model was missing it, just because like the features I built were not designed to detect Nissan Leafs because you know most cars were Teslas. So that was one thing I found. Also geographically, like the areas where you tend to expect, you know, higher cost of living, higher home prices, that's where more EVs were located, as you would expect as well.
But did you get like interesting false positives, things that looked like EV charging that weren't?
Yes, so I did look, so we actually did this work somewhat in competition with a third-party vendor. So I did look at their, you know, their false positives in comparison to mine, you know, why didn't I get those false positives? And some of the false positives they got were hot tubs from surveys. Like we would ask in the survey I sent, we asked, do you own a hot tub? Do you own a heater? Do you own a EV? It wasn't just like, do you own an EV? And so a lot of their false positives were hot tubs.
Thank you.
As someone who has a electric heat pump and a hot tub, but not an EV, definitely something that's sample. So I'm going to ask the last question again, because it's that priority. But have you thought about when or how often you're going to retrain the model, or how you're going to monitor the model as you know new EVs come to people's houses, possibly in the same neighborhood, possibly in different neighborhoods, et cetera?
Yeah, we would love to retrain the model and do stuff like that. In terms of like timing of when that's likely to happen, it's probably not going to happen for a long time because we're right in the middle of like a data lake MLOps huge transition within the company that's probably going to take over a year. So I'm not going to try to do anything like that until that's all settled.
Sounds like a wise decision. I've been in those situations. Other questions for Andrea? Anything online? Eric?
No.
Yeah.
I just have a broader question. Does every electric company in the country or energy companies have their own version of this? And do you collaborate with them?
Yeah, so that's a great question. And that's kind of why I brought up this idea of that we're an investor-owned utility. Like a lot of utilities are public-owned utilities, and there's no competition here. So everything I do is public. Like I can definitely share all my work with other utilities. However, there are third-party vendors that sell this as a model. Like we can detect EVs in your service area, and I'm like, hey guys, let's work together. Let me talk to our electric utilities. Like we don't need to do that. I built one here. Let's work together. The issue though with, it makes it hard to collaborate with other utilities is that like security is like a huge thing here. Like there's so much security within the company. Like recently we were not able to like record phone, we were not able to do video recording anymore because of security concerns. So like, that's one of the that makes one of the things that makes it difficult. Another thing is that, a lot of utilities, like they're not really funded to do this innovative work. They're funded to keep the lights on, and, safety is the most important thing. And so, uh, it's hard to, for them to find the bandwidth to do things like this when there's a vendor that's just going to provide it off the shelf for them. They don't, it's hard for them to make the investment, and like we got to hire data scientists, and we have to understand our data, and now we have to build a whole new data infrastructure. So that's what makes it tricky to like share this work.
Andrea, I'll add on to that. So I'm a consultant for Pacific Gas and Electric, so the big electric utility in Northern California. And I've seen some very good, not with PSE yet, but I will definitely be contacting Andrea later. But we've had interaction with other utilities around the country about modeling, about these kinds of sensors. Hey, we're thinking about buying this platform. Florida Power and Light bought this platform a year ago. How do they like it? Because there's somewhat of an old boys club, and people have been studying this, working utilities around the country for decades. And so yeah, I work with people who have interacted with, or even come from other utilities, and they bring their knowledge and insight. So there's certainly some of that. As far as like an academic sharing, the IEEE is a lot of where these people go to publish papers for conferences. So I'll be going to those, which is kind of cool. I hope there's some good interaction there. I don't know if you or your team goes to those things, but that'll be fun if y'all do. And so there's certainly some of that. But certainly privacy, safety, messy data, and yeah, some of these places are fully public, some are public-private. PG is in a similar state to PSC, where it's a what's called a natural monopoly, but it's a public-owned or private-owned money-making public utility. It's very complicated. And I won't say more, because I'm sure I'll put my mouth on stuff like that. Any other questions? We can probably squeeze in one more quick question before we move on. All right, let's thank our speaker again.
All right, so next up, we have, if I can flip to the other, there we go. And here, our next speaker is another longtime friend of ATDS, Julia Silge. And so if you want to take it over, Julia, whenever you're ready.
All right. So have I successfully shared my screen?
Maybe. Let me switch back
Okay.
to the app. Okay, she has. So now it's on me to get that up. Ah, yes, we got it.
Got it?
Looking good.
All right. Thank you so much for that introduction. I'm really so many other speakers. It is such a delight to be here and to speak to people who have the same background I have, and people who I know, including Andrea, who I go way back with. I'm excited today to be talking to you about demystifying code assistance. Well, we've heard some talks earlier today about LLMs. Mine's going to be a bit different. Very applied, maybe very basic. As I was prepping this, I was like, oh man, I hope this isn't so obvious that everyone knows all this already, but I feel like it's stuff I've learned recently, so I'm happy to talk about it. So my name is Julia Silge, and here are some places you can find me. My undergrad degree is in physics. My PhD is in astronomy. I finished my astronomy PhD back in 2005 at the University of Texas, and there, my main research that I did when I was in astronomy was in the kinematics of nearby galaxies. I was an observational astronomer. I worked mostly in the near infrared. This is Centaurus A, one of my favorite galaxies, from a paper I wrote back in the day, measuring the supermassive black hole at the center of Centaurus A that's growing and accreting there. I stayed in academia kind of through my postdoc years, then exited, did a bit of, like Andrea, a bit of work in the education space, and then landed in the field of data science a bit over a decade ago. I've been at the company where I am now for almost 6 years. It's called Posit PBC. It's the company formerly known as RStudio, if any of you have heard about the RStudio IDE. When I first came there, I worked on R and Python packages for machine learning and MLOps. So we make a lot of open source software at my company. And more recently, for about the past 2+ years, I've been working on a new IDE. So the IDE is called Positron. Positron is a next generation data science IDE. So much like things you may have heard of like Cursor and Windsurf, it's a fork of Code OSS, which is the open source software that Microsoft uses to make their proprietary builds of VS Code. So it has kind of on the similar infrastructure that these other forks are built on top of, but it's built with a different use case. Like it's built to be specific for data science. It's not a general software engineering IDE. It's specifically built for data science. It's extensible because it's built on this ecosystem. Like you can use VS Code compatible extensions with it. It's built with tasks like EDA, like exploring your data, reproducible authoring, like if you need to make data reports, publishing data artifacts. It's built with those use cases top of mind rather than general software engineering. Part of what Positron provides is a data science aware, data science specific AI code assistance. And so that makes me someone who is both a user of AI tools and a tool builder, like an AI tool builder. And I feel like I have learned so much being involved kind of on the tool building side of what it is like to have AI code assistants, like so much that I didn't know a year ago, 2 years ago, about how these models work and what it's like to use them in an AI product. And so that is what I want to talk about. So AI today does a few things well, and one of the things it does well is code assistance. So I bet everybody in this room, almost every single one of us, have like used some kind of consumer AI product like ChatGPT or GitHub Copilot or Claude Code. It does AI code assistance really well, which I think is something for us all to wrestle with as people who mostly, like a lot of what we do is writing code. It does some things very badly, perhaps most famously count things, right? Like we build a program that can't count. So there we go. So we often use these tools often without really understanding how the products work because they're new and because AI as like these large language models, they don't behave like other kinds of software, right? Like we don't really have very good metaphors to reason about why they act the way they do. Also, the AI and LLM space is just rife with jargon, and perhaps purposefully to make us think that it's like magic, you know? So I think we can counteract this widespread obfuscation with a really practical, grounded understanding of how these products work, what are the building blocks. So we can do that by understanding like the terms, like what do these terms mean, the concepts, and like the components that go into what an AI product for code assistance is like. So let's dig into that. So the first term I want to talk about is a model. The LM talks that were happening earlier today were mostly about these things. So this is is both a statistical artifact and a software artifact somewhere, and most of us interact with them as black boxes, right? Like we put some kind of prompt in and we get something back out. You can think of them as like this probabilistic representation of compressed information, often like text information. It also can involve image information, sound, and it can you poke it in some way and it like like splurt, like gives something back out at you, often text, including code, right? Like you put something in and it will get out there. So there's a whole bunch of so many models. And when we think about them, you can often feel like, oh, what are they? How are they different from each other? What are they like? So this is a screenshot of Positron, and we have Positron Assistant, which is the AI code assistant here. And I've pulled up the UI here that shows, it's like the model picker. And here we've got Claude, Haiku, Claude, Opus, Claude Sonnet. So these are all examples of models. So Claude would be like the big family, and then there are different kinds, like sort of subfamilies of models that are made available in Claude. So, and then the numbers, of course, are these different releases. So these are all example of separate models here. And here, when I've got this set up, I just am looking at the Claude models. If I were to configure this a little bit differently, I would see, oh, I've got the Claude models again, but I also have the Gemini models, the GPT models. So these are all examples of different kinds of models. The Claude models are trained by Anthropic, Gemini models are trained by Google, and GPT models are trained by OpenAI. So these are some of the like real heavyweights when it comes to like the AI companies who are actually doing the model training. And here you also can see it's actually telling me how much it's going to charge me for using these different models to do my AI code assistance here. So that's a couple screenshots from Positron. Here, one of my favorite tools these days is Claude Code. And here I've got Claude Code open in a terminal. And right now I am hooked up again to a model here that is one of the Claude Opus models. So Claude Code is an AI product made by Anthropic, and it uses typically you use the Anthropic models with Claude Code. They're really made to like work well together there. So one of the ways you customize your AI code assistance experience is by choosing a model. And I think that most of us choose models a little haphazardly, a little bit based on like what did I read on LinkedIn or what did my coworkers say. It is possible to take a bit of a more disciplined approach to decide which model you're going to use. And the approach that typically is taken for this goes by the name AI evals. So if you hear people talking about AI evals, it's talking about a somewhat disciplined way to decide what model to use or to evaluate how different models work in different ways. This is from a blog post from one of my coworkers at Posit, Simon Couch. Simon works a lot on AI tooling around R. And here you can see on the x-axis, it's like the cost, and on the y-axis, it's how correct it was. To make a plot like this, you have to have a data set of kind of gold standard prompts with a way to evaluate the prompt. Like, what are you going to say has to be in the output, or what is the characteristic of the output that you use, and how do you, and then you can judge, like, and then you run through this set of gold standard evaluation examples multiple times, and then you estimate how well a model does. So here you can see for this particular data set of examples of evaluation, we can see that maybe I might choose Claude Opus based on this because of how well it is, but you can kind of see how the performance is related to the cost here. So this is a great way for us to think about, okay, if I'm having to choose a model, what are the things that I care about? Often it's about how well it does at the task I want to do and how expensive it's going to be. A lot of the data sets that are used for doing AI evals have been around long enough that they're starting to be in the training data. So it's good to keep an eye on like what is being used to evaluate the AI there. So that's model. Think of that as the most like sort of basic building block of what AI products are built on top of. The next is model provider. So here we are back to positron, and you'll notice that right here it says, you're connected to Anthropic, and that's why I have the Anthropic models there. So some organizations that train models also act as model providers. So the examples of those would be like Anthropic, Google, OpenAI. So I have an API key to Anthropic, and so I've configured positron here that I'm working directly with Anthropic to get back my to interact with the model here. Here, I have configured positron here to be connected to GitHub Copilot. So some model providers give you access to models from multiple model training companies. So Copilot is an example here. Another one would be like AWS. So choosing a model provider is typically about what models they provide, but maybe even more importantly, your own security needs and or your organization's security needs. It's really important that you trust your model provider to have your data and that you understand what they will and they won't do with that data. It is so easy to prompt your model in such a way that actually row level data gets sent to the model provider. I would say it's arguably impossible to work with AI code assistance tools doing data science and to make any kind of promise that your literally your data is not going to end up in there. So it's really important that when you work with a model provider, you understand what they say they will and will not do with that data, and that ultimately you trust them. And that's where products like AWS Bedrock come in. So that's a product that AWS sells where they act as a model provider with security guarantees around your data will not leave some certain like security perimeter and whatnot. So IDEs like Cursor and Windsurf and Zed typically can act as a model provider. Like Cursor, the company, provides you access to a model or lets you bring your own API key. For example, if you have security needs, like you need to use AWS or you have an Anthropic account and you want to use it, so like that. My company right now does not act as a model provider for IDEs, like for our studio or for Positron, and so which you can imagine, I'm sure, is a big, complicated question. Like, should we not, like where are we going to go down that path? So we talked about model, we talked about model provider, and there's like intersections here that end up impacting your AI code assistance experience. The next thing I want to talk about is tool calling. So tool calling helps extend the capabilities of an LLM by allowing it basically to interact with the real world, to like call external functions or APIs. It's really useful in code assistance, but in basically anything you might want to use an LLM to do. Like anytime you need to retrieve some information for somewhere, take any kinds of actions or have any kind of information that's beyond what's built into the model and its training data. That's where tool calls come in. I'm going to show you two diagrams to kind of talk about how do tool calls work. So this is how tool calling doesn't work. This is how tool calling does not work. But sometimes I think this is how people might think that they work. So I, as a user, say, hey, what's the weather right now at Fenway Park? I go to the assistant. The assistant says, the weather at Fenway Park. I'm going to make an API call to the weather service and then get back a value. And then I will respond in natural language back to the user. So this is not how tool calling works right here. Instead, this is how tool calling works. So I, as the user, say, in my prompt, I say, hey, what's the weather at Fenway Park? And also, I have a tool available for you to use. This tool is a tool that is like a function that's like get current weather. And get current weather does the API call to the weather service. And so I say that to the LLM. The LLM says, they asked me about the weather. I think I can use this tool, get current weather, to do that. And then the LLM says, we're going to call get current weather with the right kind of inputs. Typically, the way tool calls work is they're run by you as a user. Like you are not literally running it, but the LLM is using you as a user to like do the tool call, run the code or whatever it is. And so then it goes to the weather service, gets a result from the weather service back to you as a user. You may not see it unless you dig into logs, but then that goes to the LLM, and the LLM says, oh, I've got this JSON here. Let me make a natural language response to get back to the user. So the first diagram is not how tool calls work. This is how tool calls work. You basically give information to the LLM about the tools that are available for it to use. The value that the chat model brings is not in helping with execution, but rather with knowing when does it make sense to call a tool? What values should you pass as arguments? And how can I use the results from the tool call in formulating its response? So let's look at positron here. So this is positron. I want to highlight here where it says configure tools. So these are tools that are available in positron specifically, since we, like, the whole list of all these other IDEs are all forks of VS Code. Some of these are things that we inherit from upstream from VS Code. They're things anybody who writes code needs to be able to, for example, get the project tree, right? Like, what are the files that are in my current workspace? Or being able to run a task, like in the VS Code sense, right? Like to be able to run some kind of task here. There are some of these tools that we built because they're more about doing data science. So one of those is like get table summary. So if you have a pandas or a polars data frame, can I get a summary of it and pass that to the LLM so that it can help you with your exploratory data analysis task? Or get plot. So these models that are good for code assistants often are also good for, they're multimodal models, meaning they can handle not only text, but images as well. And so you can take a plot that you've made and send that to the model provider that has your model, and then it can summarize it for you, give you some description about it, give some advice of how to improve it, or whatever it is that you would like to do that here. So these tools are all tools that are available here that are specific. If you are a Claude Code user, you may have experience with you say something and then it decides to, oh, I am going to do git diff, or like, oh, I am going to do ls, like you're going to do things in the terminal there. And so it is running those are tools that have been made available to Claude Code, things that Claude Code knows about that it can do, that then get executed on your behalf. You and the assistant see the output, and the assistant can summarize the output in natural language for you to know what to do. So that brings me to my next term here, which is agent. What does agent mean? This is the one that I think right now, here at the beginning of 2026, that is feels the most jargony. Some of the AI companies talk about agents in some pretty mystical ways, and I think perhaps here today is where we gain the most by rejecting hype and being really specific about what it is that we mean. And so I am going to use a definition that comes from Simon Willison's blog. I highly recommend following Simon Willison's blog, or via whatever method you prefer here. So a couple months ago, he had a blog post where he gave a definition of what agent is. And so here he says an LLM agent runs tools in a loop to achieve a goal. So agent is not mystical magical, but rather can be super effective because it is able to run a tool, see the output of the tool, decide to call another tool in a loop with some goal that it is in pursuit of. That the agent is like, oh, okay, am I getting closer to the goal? Am I like, what should I do next to get closer to the goal? So this is I think the most helpful definition I have heard of what agent is. So Claude Code is often spoken of as an agentic AI code assistant tool. Similarly, the copycats like Codex and other kind of things there. They're usually in a terminal, and they are LLM agents that have access to a lot of tools, and then they can run those and see the output and then decide what to do next. I think the idea of agents in data science is really interesting. And if you're interested in like data science specifically and agentic tools for data science, specifically when it comes to exploratory data analysis, you might want to check out DataBot, which is a new AI code assistant product from Posit, my company, that's built with our sort of a specific opinionated take on what a purpose-built tool for this might look like. It's a really good example of how these components all get put together to make a product that you use. There's a model down at the bottom, and you do get different results depending on which model you use. The model is provided to you by some model provider. There are tools that are available to the model to decide what to do. And then there's some sort of driving goal, and the agent has the ability to run tools in a loop here. It's interesting for exploratory data analysis because the goal there is somewhat you might argue like it's maybe underspecified perhaps because when it comes to exploratory data analysis, we don't know ahead of time what we're going to find in data. It is more like the process of science that all of us kind of came up in our training and understanding. We don't know the answer ahead of time. So I'll throw up a few links here. If you're interested in trying out Positron, there's some links here. It's also available as a professional product if that is something that is a good fit for you. But high level, what I was really excited to talk to you about today was that, like I think demystifying how these tools work, like helps us understand these AI tools, and that helps us both use them more effectively and more responsibly. And it also empowers us to build on top of these technologies, to ourselves become AI tool builders. Like, when are these things legitimately useful? And with that, I will say thank you very much and see if there are any questions.
Thank you very much. Thank you.
Code or evals for, using, GitHub Copilot, whatnot. You mentioned that earlier in terms of how to choose what model. You can hear me by the way, right?
I think so. Yeah.
Yeah, so you said, that we shouldn't just rely on vibes to choose which model, but we should have some approach, and we could look at evals. And my question is, how the impression I've had is that a lot of these evals are on short, well-defined tasks a la leak code, whereas at least when I'm using these tools, I'm working in a moderately sized code base. I have a general task, and I want it to look across the code base, generate a plan, I approve or tell it to modify that. It's like this kind of, I assume, more diffuse large-scale thing, which is harder to put into a simple eval. I was just wondering if you have any thoughts about that in terms of how good they are or how you think about this.
Yeah, that is a really very a very real challenge in how we use these. And I think most of us today are making these calls based on some combination of some more quantitative data and what we hear from our coworker and like what we understand the community to have best, like, to be kind of like what is best state of the art right now and that type of thing. So and I especially think some of the like classic software engineering tasks, like the data sets, they are in the training sets now. Like the older ones, it's like it's not very useful to look at them anymore because it has been we're overfitting to those things that are in those particular data sets. I do like actually the more bespoke, like the kinds of things Simon did where it's like he went and he did it himself, and maybe it's not as big a data set, but it's new kind of stuff, and I find it very I find it very interesting how things do when it comes to that. It is true that in general, the same models do better on a category of tasks. Like you saw Opus at the top there, right? And like the new Opus model is in general across languages, across like people are like, wow, huge step forward, really having a good impact here. So there is transference there, which I think tells us a lot about how programming languages are I mean, part of the reason these things are good at code assistance is that the programming languages have a limited set compared to natural language, right? Like they have a limited set of vocabulary and meaning, semantic. Like there's a more limited set of semantics in code compared to and so they tend to transfer pretty well. There are language to language differences in how these things do, but it tends to all come up and down together. It's kind of rare for you to find you're like, this model is super good at my Erlang code, and it's bad at Python. Like that kind of thing doesn't tend to happen. Great question. Great question.
Thank you.
Looks like Andrea online, you've got a question?
Yeah, great talk. Thanks, Julia. So in my company, we have LLMs like that the company uses internally, like to help with writing emails, summarizing reports. Not so much with writing code, although we do have that as well. Do you have any advice for encouraging like the team in my company that builds these to do these AI evals? Because I just don't feel like they're done. They just tell our customer, they just say, here's a model, just use it. And how do we know it's good? How do we tell the people using it which model to use? What's appropriate for what? It just doesn't feel like it feels like all of a sudden with LLMs, like people stop doing training test validation. Like,
Yes, yes. No, no. I think this is a really interesting question or like a really interesting thing to wrestle with because it's about like it's like, oh, it's new and fancy and it must be good. And you're like, what? What? So there are the people who are doing, I think, the best work in like what is an AI eval they have this course they do, and I will find it and drop it in the chat here because I do think it's actually like it's very interesting what is involved, but like it is like back to almost pre-big data days in terms of like you have to actually create the data set to do the evaluation because there are tools around like every time a customer complaint comes in about the AI product that you built, right? Like come in and keep that. Now that's really valuable data for you to use in times of like your eval. Their course is kind of about like oriented to people building AI products. So like someone like me, right, who's like I'm building something that kind of sits on top of the LM, like that helps people do some kind of specific things. I do think that the kinds of products that are being put into like email and doc writing like they are a very mixed quality. They are very mixed quality, and I think people are having very mixed results using them. And it is a little more difficult as a user to be like if you're not involved in the like product piece to be like I demand to see the evals or like I want to evaluate it other than on just sort of personal experience of like this one was good most of the time, this one was less good most of the time. I think that it is another area where like even in the evals it is an area where work using them for code assistance is much more straightforward than using them for other use cases. So that I think what your question highlights is uh, a real challenge in like how are we using these in real applied and like who is benefiting at all from using these versus it not being a responsible use of these tools.
thank you. I've asked them like, well, why can't we just create our own like, evaluations? They're like, oh, well, let's just use the LLM to make one. And I'm like, oh my gosh.
Yeah, so LM generated um cases tend not to be very good compared to like it's like no we're now back to curating our own data set. What the thing that has actually turned out in my experience to work not badly is to have you have maybe a response from one LM and you have your prompt, you have your response, and then you have like an evaluation criteria. A separate session of an LM that didn't do the prompting, right? But like a fresh they do actually a good job of evaluating. So they actually do a pretty good job of evaluating another LLM's output. Like you give them a rubric, you give them an input, output, and a rubric. They actually do a pretty good job of scoring. But they do in my experience, a bad job of generating good and bad examples.
Oh, okay, thanks. That's helpful. Thanks.
Yeah, this feels like the difference between grading your own homework and, grading the other students in the class's homework. All
I
right,
like
one
that.
more question here.
Hi, Tony Paul from Carnegie Observatories. So I'm kind of new to the tool terminology. I think you explained it really well in terms of the Git weather tool example. So in terms of coding, I know you had a slide where you listed, all the tools loaded into Positron. I guess what are some examples of tools you would use in conjunction with an LLM for coding?
Yeah. So when I do more data science work, I'm often in Positron, right? Because that's like dog fooding. We gotta figure this out. And so a tool that you typically don't explicitly say use the get plot tool, but I might, for example, say like maybe I'm iterating on a plot and it's like I start to make the plot. I'm like, oh, okay, that's pretty okay, but what if I were to, instead of having like one line across it, I was like, oh, I want to have separate lines for these different variables that I have in my data set. And if I said that, or like I typed that in the assistant thing, I was like, oh, I want a separate line for, let's say, this kind of galaxy and this kind of galaxy. And then it might do it and it like makes a guess at what the code should be and it errors out. And then it looks at the error and it says, oh, I have the variable names wrong. And then it would do the tool call to say, give me the structure, the metadata of, say, the pandas data frame or the polars data frame. Like that's an example of like when the tool would get called because I would be trying to do something and something wouldn't work. And it'd be like, oh, I need more information to be able to write the code that will make that plot. I spend a lot of my time now doing more software engineering kinds of tasks. And I don't think Claude Code is very good for data science, but I do think it's very good for doing more strict software engineering kinds of tasks. And like I was doing something today and I was like, there was like something was going wrong with our GitHub Actions that runs our tests. And I was like, oh, I see that that's failing. And it's like the permissions are not right or something. And it's like, what? And I was like asking, I'm like typing into Claude Code at this, and then it ends up like calling a tool that was like called something on the GitHub API to get exactly which user was like running the test and it gave me exactly the characteristics. So it like called the GitHub API. I'm like, such and such is broken, and it's like, and this are like what I'm seeing. And then Claude Code decided to call the GitHub API to get the details of what user was running the test. And then I was like, oh, okay, that's a problem. Like that, the such and such permissions need to be changed. So those are the tool calls are a big part of how any AI product works, including the non-code ones, like ChatGPT, for example, has many tools it can call just as a normal consumer product. But you don't typically say, call the get plot tool or call the GitHub API tool. It's like in the process of you using natural language, the LM can, because it knows what tools it can run, it like chooses them and chooses the inputs. And then it gets the output and, shows that back to you.
Great. Those are useful examples. Thanks.
All right, let's thank our speaker one more time.
Thank you so much.